So the third session of geometrical optics, people, we will start with a quick recap of the important formula that we saw last time, which was the real depth apparent depth formula, and how it can be applied both ways. Just a second. Yeah, so how it can be applied in both ways. So basically, let me put up that formula in a slightly different way. So suppose you have a situation where we have a plane surface like this, which is separating two refractive medium. So like this, which is, this one is medium B, let us say, and this one is medium A. And there is an object in medium B, point object over here. And there's an observer in medium A who's getting what we call the normal view. That means his line of sight on the object is normal. But as you know, that image construction doesn't happen with only one single ray. So even though the normal ray, the one which is incident at an angle of 0 over here, was undeviated, okay, but it is not going to happen in such a way that only that ray will be responsible for seeing the image. There will also be what we call the paraxial rays. So by considering the paraxial rays, we had seen that the image in fact appears to be somewhere over here, assuming that B is a denser medium compared to A. So if the real depth of the object was X or D or whatever, then the apparent depth X prime or D prime or whatever worked out according to this simple formula. It was X divided by refractive index of B with respect to E, which also translates to X into mu A by mu B. So it's not only the case where you're looking from air into water or something. You could be in some other medium. This could be water, this could be glass. So your both mu A and mu B are different values. Okay. So here it is very important that the refraction is happening from medium B to medium E. So the sign convention that the notation that we are using, B with respect to A, B is the medium here in which there are the incident rays, and A is a medium in which there are the refracted rays. Okay, so that is the notation. So B is the medium in which the incident rays are there, and so as you can see, if mu B is greater than mu A, that is denser to rarer, then it will be a case where the apparent depth is shallower than the real depth. It's less. Okay. Whereas if we have a situation where mu E is greater than mu B, that is, it's going from a rarer, denser medium, then the rays bend the other way, and X prime actually becomes greater than X. So this was the final thing that we looked at last time, and today we'll start with some questions which have the application of this. So I'll straight away start with some of the questions which I've been understanding as your doubts, okay, because I've been getting messages all week and stuff from you. Okay, so, and I mean, using these questions, you will be able to solve everything that I've given in homework. Okay, so let us combine this concept with the plane mirror concept now. Okay, so we have, let us say, this is a glass slab. So this is a glass slab with refractive index. There is a problem like this in part of what I've given you. So 3/2 is the refractive index. Now it has a thickness, let us say, of 24 centimeters exactly. Okay. And now what we have done is very interesting. We've silvered from the outside this surface. So it is a perfectly cuboidal kind of glass slab. So all the edges are at 90 degrees and plane surfaces. Now this part now acts like a plane mirror as a result of the silvering that we've done. So this part acts like a plane mirror. And now there is like a point object kept somewhere here, where it's at a distance in front of, let us say, 18 centimeters. So O is a point object, and there's an observer behind O whose line of sight is normal. So what we have to do now is we have to find, so first of all, draw a ray diagram. to express the various phenomena, that is refraction and reflection, occurring due to the silvered slab in front of the object. Okay. So O is a point object. So that's the first part. So just a rough kind of ray diagram to understand the phenomena. Now we have to calculate the position of O's image seen by the observer who has a normal line of sight. Okay. With respect to O, that is from the actual object, he sees an image somewhere behind. Okay. So we have to find the position of that image with respect to the original object O only, as seen by this particular observer. So I'm just minimizing it so you can see the whole question and understand what I'm asking for over here. So just start with the ray diagram. Okay, we will solve this question, and we will see that using this as a template, you will be able to solve all the questions which are similar in HCV, etc. So don't worry about sending in your doubts right now, because I'll be discussing all the tricky questions from HCV. So that will cover, because each person has a different set of doubts. So I'm just taking a common set. So just try out the ray diagram first. Okay, try to understand how many times different phenomena are happening, and those phenomena involve what kind of situation, bending towards the normal for a refraction or away from the normal for a refraction. Then we will see how to apply calculations to that and how we can get the position of the image with respect to the object, the final thing. Okay, so let's understand the ray diagram to start with. Hey. All right, so now you can see that if I put a point object here, remember this side is silver. So let me draw a principal axis first. This is like the normal ray's path. So a ray along this path will actually just retrace its path because it's incident at a plane mirror. So it will just come back undeviated. So anyway, this is just for a guideline. So the ray that actually goes along this path, which is the normal axis, will just retrace its path. So we need not bother about that, because if we have an incident ray going in this direction, it goes undeviated, reflects back with 180-degree deviation, and then comes back undeviated. So it just retraces its path. But now what we're more interested in is paraxial rays, that is rays which are very close to this normal, but they are almost parallel, but they are not parallel. Okay, and they are very close to it. So they are making very small angle of incidence. So we are interested in that kind of rays. Okay. So now just imagine in my diagram that this is actually paraxial, though it is not, but this angle, imagine it's very small. So such an incident ray will, after refraction over here, deviate in such a way that it will bend towards the normal, because it is going from air to glass. So towards the normal means, like, let's say it would go somewhere here. So when I produce this ray back, it should meet the principal axis somewhere here. So now in this diagram, this is a produced back ray. So I'm just showing it with a dotted line. Whereas actually, this is the incident ray coming from the object O. And this here is the first phenomena that is happening. There is refraction from air to glass. So we'll do the numerical solving of it also. But right now, let's say I'm just first interested in understanding the location of the image and all that. So wherever this intersects the principal axis, the ray produced back, the refracted ray produced back, let's say that is I1. Okay. Now next what is happening is that the ray incident on the mirror, which appears to be coming from I1, that's reflected by the plane mirror. So it will produce an image of I1 behind. Okay, so the reflected ray now will look like this. The reflected ray, let's say, so my diagram is actually not very accurate. This distance should be equal to that distance. That's happening because I have, let me see if I can. So just imagine this ray is a little bit more like this. So this is the second event which is happening. This incident ray, which appears to be coming from I1, is reflected by the mirror. And when you produce this back, let's say, it gives you an image somewhere over here. But even that is not the final image, because you can see these rays are not coming back to air. So they're not coming back to our observer. So this image is I2, let us say. So these rays will once again suffer refraction. And they will bend this time away from the normal. So they will go like this. Okay. Such that when you produce this back, let's say, it intersects the principal axis somewhere over here. Now you see, using this diagram, I will get the final image. Because the final image is constructed by these rays, the ones which are out into the air again. So these, now just consider paraxial rays like this. So these rays are actually very close to your principal axis, because these angles here are very small, these angles. Okay. So they will all intersect, produce back to this kind of point, and this becomes the final image. Okay. So you can see that this is the site of my first phenomena. Okay. This is where my first refraction occurs. Then this is my reflection. And this is where finally the second instance of refraction occurs. And 3 events in all are occurring. Okay. So I'm just minimizing this a little for you to understand the detailed ray diagram. So again, for JEE level questions, your ray diagram should have clarity, even though you're not doing subjective questions, but you can have questions where you have to select the proper ray diagram and all that from the options. So you must understand fundamentally what is happening in terms of reflection and refraction. So that is a very important part of your geometrical optics. Just to answer, I think I'm again and again getting a lot of questions about doubts and doubt sessions and all that. People want to make it very clear over here that today's session will clear all your doubts. Okay, just have the confidence in that. I cannot clear everybody's doubts in 5 minutes. Okay, so just have the confidence that by the time today's session is done, your doubts will be clear. Okay, so this is the ray diagram. Now let us see how we will solve each and every event. Okay. So for solving, let us also label these points. Okay, so this point is, let us say P, and this point is Q. Okay, and so far the two things we know is that this distance is 18 centimeters, and this distance, the slab's thickness, is 24 centimeters. So now we will have to solve each event one by one. So I will just put up how to solve, and then you try it yourself. Okay? So the first event, if you follow the ray diagram, the first event that is happening is that it is refraction from air to glass. Okay. For that, the object is the actual object O. So the real depth is equal to the distance OP, which is given to you as 18 centimeters. Now the image, if you follow our ray diagram, is what we have labeled as I1. So that means that our apparent depth is equal to I1P, and you will use that real depth apparent depth formula. Okay. So you use that formula and you will get the position of I1. Now the next thing, the second event now. So immediately after this refraction, what is happening is that the rays which have refracted into glass, they go and hit the mirror. So for the mirror, which is the incident ray, this refracted ray inside glass, that is the, I'm just showing by the pointer. So this ray is the incident mirror ray for the mirror. So this incident ray is actually coming from where? It's coming from I1. It's not coming from O, because there's been a bending in between. So these rays appear to be coming from I1. So for the mirror, as the mirror sees it, what is the object? It is not O. The object is in fact I1. So I1 becomes the image, becomes the object as far as the second event is concerned, which is the reflection. And laws of reflection tell you that it will reflect such that angle of incidence is equal to angle of reflection. So I1's image will be produced behind the mirror at I2, such that the object distance, which is QI1, will be equal to the image distance, which is QI2. So that is how we will solve the second event. Okay? So the second event is reflection at plane mirror. Okay. So for that, the object, by the way, is not the original object. It is the image of the first event. Okay. And the image is I2. Okay. So we'll use the concept that object distance is QI1 on this side and image distance on the other side is QI2. So by using the fact that in a plane mirror reflection, image distance is equal to object distance, you will be able to find the position of I2. Here you found the position of I1. Okay. And then you come to the third event, which is now refraction. It's the second refraction of our system, but overall it is the third event. So it is refraction, and this time from glass Let's understand that refraction. So your reflection is over. Now these reflected rays, after reflection, they are going and getting incident where on the glass air interface. So they are bending away from the normal lines. So these rays are actually coming from what? As far as this interface is concerned, what is the object? It is the position from which these rays are coming. So that's nothing but I2. And after refraction, they are diverging further such that you have to produce them back to get the virtual image at I3. So for this third event, what is the object? It is I2. And what is the image? It is I3. And totally there are 3 events only. So I3 becomes your final image. Okay. So for this, the object is I2. So since it's a refraction at a plane surface, we need that real depth apparent depth formula. So the real depth of the object from the from the surface of refraction, that is actually the quantity Pi2. Whereas the image, which is I3, and that by the way will become our final image for the system. Is Pi. So again, I'll have to solve using the real depth apparent depth formula for refraction from glass to air, given the refractive indices and all that. And from this, I'll calculate the position of I3, and that is the final image. So what the question is now asking is the position of the final image with respect to the object. So that is nothing but I3O, that distance from O to I3, I have to calculate that. So I'm minimizing this for you, and what I want is that now, given the 3 events which I have clearly written out like this over here, you are able to substitute the values and correctly apply the formula and tell me what each of these results are over here. Where is the position of I1, where is the position of I2, and therefore where is the position of I3, and from that what the final answer is. Okay. So the reason why I'm doing these questions is because these questions are basically supersets of all the questions which I have given for homework. After this, I will show you in which question in HC Verma to use which formula or to use which kind of concept, and you will be able to solve all of them. Okay. So please don't keep telling me that my doubt is this, my doubt is that individually, because I that way I cannot, if I start looking at each person's doubts, I cannot solve it all in one session like this over here. So you have to be patient, work through the whole session, understand each and every concept over here. I will tell you how to relate these concepts with the questions given, and then out of those questions, whichever ones your doubts are, they will have got solved. Whichever ones you solved before, well and fine, you don't need to even listen to that part, right? Okay, people, has anybody got the final answer? Ashwin is close, but just a bit of modification. Okay, your matlab, see, your answer might be correct as far as the position of the image behind the mirror is concerned, but then there's also a third event, so you have to solve that also. So maybe you are giving me the answer for I2, but remember the final thing is I3 now. So that's why a bit of adjustment. Remember, refractive index of glass is 3/2. You have to use the value of refractive index of glass as 3/2, and air is of course 1. Remember, if I have given that before, yeah, I have given that earlier to 3/2. Okay. So I'm very soon going to start putting up the formulae for each of these. What formula I'll be using here, what formula I'll be using in the second one. But before that, I'd like you guys to try this out and try to get the answer. The distance between the point O and I3 finally, how much that should be. Okay, so anybody got the answer yet? It should be 68 centimeters. Okay, the final answer should be 68 centimeters. But let me solve each part. Okay, so for the first refraction, what is happening? It is air to glass. So the formula will be that the apparent depth should be equal to the real depth divided by refractive index of air with respect to glass, because it is from air to glass. Okay, remember like that. So that will actually be refractive index of glass multiplied by real depth. Okay. So that is why if you go back to the earlier diagram, you will see that Pi1 should be equal to Po multiplied by refractive index of glass. So this should become 18 into 3/2 or 1.5. Okay. So this will become 27. I'm just referring this back to the diagram and just clarify what this calculation is giving. So see, real depth was Po and the apparent depth was I1P or Pi1. Okay, this one, just this refraction. So Po is the real depth and it's bending towards the normal. So it diverges less. So when you produce it back, it goes to a further behind point. So that is why your apparent depth your apparent depth Pi1 has to come greater than Po. Okay, so that is a clue. So that is your first thing solved. This is the first event solved. Okay. Now similarly, now let's come to the second event, which is very easy. The second event is a simple reflection, so it will be very easy to solve. It is a reflection at plane mirror. Okay. So the image distance should be equal to the object distance. So the mirror's pole was in fact the point Q and the image was I2. So I2Q should be equal to I1Q on this side. And I1Q is nothing but PI1 plus the thickness of the glass slab, PQ. So PI1 we just saw is 27 centimeters and the thickness was 24. Okay. So this is becoming 51 centimeters. Okay. So this is not the final image, remember, even though the reflection is happening, but this is QI2. So this thing. Okay. So what we had done earlier is now we had calculated what all we have calculated. Now I'm just labeling with a different this thing. So this distance we had now calculated as 27 centimeters. Okay. Now as far as this plane mirror is concerned, object कौन सा I1 है, तो उसके लिए object distance क्या हो गया? उसके लिए object distance ये वाला हो गया for the second event. So the object distance is 27 plus 24, which is 51. So पीछे image distance should be the same. This distance should be 51. Okay. From this point, it should be 51 centimeters behind X. Okay. And now try to solve the third event yourself. It's like you have the rays inside glass. They are coming from here. So they are coming from a depth of how much? 24 plus 51. They are coming from that much depth. And they bend away from the normal going into air. So that gives you an image over here. So this I3P is your apparent depth. Okay. This distance I3P is your apparent depth. And I2P is your real depth. And the refraction is happening from glass to air. So use the formula of refraction from glass to air. And the apparent depth, real depth formula. So once you do that, you will be able to work this out. Okay, people. So anybody got the final answer yet using this? These are the first and second events solved according to the ray diagram made above. Okay, so let's solve the third event. So the third event involves refraction at a plane surface, but from glass to air. Okay. And for this, the real depth was PI2. So that distance, if you go back, you can see I2 was 51 centimeters behind the mirror, and the mirror itself was 24 centimeters wide. I mean, the glass was 24 centimeters in front of it. So from the glass air interface, the distance of I2 is nothing but the distance from the mirror to the distance between the two sides of the slab, which is 24. So that is coming out to be 75 centimeters. And the apparent depth is PI3, which we are trying to calculate. So now we'll use the proper formula that the apparent depth is equal to the real depth divided by refractive index, this time of glass with respect to air, because it is from glass to air. So the formula may, the refractive index in the denominator is this. So that is why your PI3 should become 75 divided by refractive index of glass. That is 3 by 2. So 2/3 of 75, so that is 50 centimeters. So PI3 is 50 centimeters, means that OI3, object to final image, is just 18 centimeters plus 50 centimeters, because the object was 18 centimeters in front of the glass slab. So that is 68 centimeters. This becomes my final answer. The position of the final image with respect to the object, that becomes this. So I'll just minimize this calculation and I'll also show it to you in context of the diagram. That is fully clear. So just take down the calculation and the value, so that when I refer to the diagram next, you can clearly understand which one is which. Okay, so if you've taken down the equations, let me take you to the diagram. Let's understand this again. So in the diagram, we have to just focus on this part, the second refraction that is happening over here. So here, second refraction ke liye, where is the incident ray actually coming from? This one, which is incident. So just follow my cursor. So where is the incident ray coming from? So the incident rays, if you pull it back, it's coming from I2. I2 is of course a virtual point. There's no actual object over there. Okay. But it's a case of, again, what we call virtual object for this, because the rays are coming from a virtual point behind a mirror. So anyway, so so to this interface, on that side you have air, on this side you have glass. So to this interface, the object is nothing but I2. So what is the real depth of the object? It is this distance, PI2. So PI2 is how much? It is 24 plus 51, that was as 75. And now it will bend away from the normal like this, that when you produce the refracted ray back, it appears to be coming from I3. So for somebody standing here, the rays coming from here don't appear to come from I2, but they appear to be coming from I3. So this point's image appears to be over here. It's all virtual, of course. All these images are virtual. Okay. So I3 becomes the final image. Now, how do we find the distance of I3 from the point P? The real depth apparent depth formula. So the real depth is 75. The apparent depth will become 75 upon refractive index of glass with respect to air, because the refraction is happening from glass to air. So it will be 75 divided by 3 by 2, or 50 centimeters. So now we are getting that, okay, I3 from the point P is 50 centimeters. And what we needed to find out, the positional image with respect to the object as seen by the observer in front. So that is nothing but OI3. Okay? So that is 50 plus this 18. So that is becoming 68. So that is the final calculation of this. Okay. Now there are a number of questions in your homework And many of you have been asking about these questions with doubts and all over the week. So I have given some hints so far, but now with this it will be clear to you how to exactly get the calculation also. The hints were just, I was telling you what formula to use and where to use that, but now you'll see actually how to implement the formula. Every case is there in this. So anything where there is refraction at plane surface and may or may not be combined with reflection, like this one has reflection combined, you'll be able to solve using this. So I'll just tell you from HC Verma which are the questions which are relevant, which you can solve using this very concept, using this question as a template. Okay. So if you see all these questions like 19, 20, 21, in 22 has this thing, mirror plus refraction, plane mirror plus refraction. Okay. These questions are all related to this kind of concept. 23 even. Now in between there are some questions which are different, so I'll come to that also. And of course before 19 there are questions involving spherical mirrors, so I will come to that also. Okay. But spherical mirrors we've already discussed earlier, so I'm okay. Now let's come to a question involving spherical mirror along with this thing, along with refraction. So the next question I'm referring to will be similar to questions like 11, 12, etc. and HC1, the ones before this where there is this thing involved. So let's see a typical example like this now. Now this is a very critical kind of example. Again, it will open up a lot of questions from your homework exercise by just understanding this. So what we have here in this example is we have a concave mirror like this. Okay. So this is concave mirror of radius, let us say 60 centimeters. Okay. Now what we have also done is we have filled the concave mirror up to a certain small but significant height with water. So there's a layer of water above and obviously gravity, so the surface of water is plane. So this is a layer of water and the refractive index of water is given to us as 4/3, such that this distance here from the pole of the concave mirror to the height of water, this height of the water layer is, let us say, 2 centimeters. Okay. Now what we want to do next is on the principal axis, somewhere above, we want to place a point object or like a point source of light, like a small LED bulb or something. Okay. Such that something very interesting is going to happen, that the whole system, that is the water with the concave mirror behind it, is going to reflect back its light, and that reflected light should be thrown back at the object only. So that means the final image should coincide with the object. So we have to apply that condition now. So this is a very common type of question, common theme of question, where the final object coincides with the original, the final image coincides with the original object. Okay. So here I am placing a point object, like a point source of light over here. Okay. So now the question states that at what distance from the pole should the point object O be placed? Okay. So O is a point object. You can even think of it like a point source of light, like the tip of a candle or something, such that its image due to reflection coincides with the object. So find the distance OP at which we should place this. Okay. So I would like you to attempt the question in the very similar manner like we have done in the previous one. That is, first draw a ray diagram and understand what all phenomena are involved. and from that, then apply the calculation of the relevant formula. So you'll see the only formula that will change for you while you are applying is the reflection formula. You cannot use the plane mirror concept anymore. You'll have to use the UV formula for spherical mirror for this. Okay, so hope the question is clear, people. Just try this out and see if you can get the answer. I'll give you the answer, then we'll discuss everything, including ray diagram. Just as a hint to you, I'll tell you that, see, whenever we want the final image to coincide with the object, in the case of a system, always we want the rays to retrace their path. Only then the final image can coincide exactly where the original object is. So the final rays that are coming back into air, after going through this whole system and reflection and all that, they should retrace their paths. So retrace the path kab hota hai? When there is what we call normal incidence at a mirror. That means the rays incident at a mirror should be incident at 0 degrees angle of incidence. Okay, so there's a concept of retracing the reflected, the reflected rays should retrace the path of the incident rays. So retracing the incident rays in a reflection. So what is the condition for that? The condition for that to occur is normal incidence. So just as a hint to you, what is the meaning of normal incidence? Let's understand in each type of mirror. So for example, in a plane mirror, normal incidence means this. So this is what would be required for retracing the path. In a concave mirror, normal incidence would mean this. So that means this must be coming from the center of curvature. Okay. And same goes for a convex mirror also, but though it looks a little more tricky because the center of curvature is behind. So in this case, if I want normal incidence and therefore the rays to retrace their path, the ray should be incident like this, such that if you produce it forward, it will go and meet the center of curvature. So that means it will retrace the path. So this is a very important concept over here. So in any situation where we are having this thing, that their final image coincides with the object, that means there is retracing of path happening. So if there is retracing of the path happening, there has to be normal incidence. So in this case, it's a concave mirror. So I want this situation. Okay, I want this situation. So just use this concept now. Along with, of course, remember here, not only reflection is happening. Before reflection occurs, there's also a refraction happening. So you have to take care of that. Okay, so use that along with the formula. Yes, I have just got an answer from somebody, Austin. No, see, the answer, Austin, would have been radius of curvature had there been no water. If there's only the concave mirror sitting like a bowl, और उसके ऊपर मैंने ऐसा एक object रखा है, so then the object should be at the center of curvature. But here, before the light reaches from the point source or the object to the mirror, there's also something else happening in between. There is refraction from air to water. So we have to take care of that. Now that refraction is happening at what kind of surface? It's happening at a plane surface. So which formula we'll use? The real depth apparent formula. So that is the hint for you to solve the question. So just start with a ray diagram for this particular case and see how it works out. You will be able to find the answer very soon. Okay, so let me just carry this ahead with the ray diagram. Then you can try the calculation finally yourself. So my ray diagram will have to look something like this. Now let's say my point source of light is here. So now any ray of light incident from this onto this will tend to bend where? It will tend to bend towards the normal after refraction at the plane surface. It will tend to bend like this. So it bends a little bit like this. Okay. Such that when you produce this bent ray backwards, it appears to be coming from a different point. It appears to be coming from a point here. So I'll just draw the principal axis for further clarity. Start with the principal axis actually. Just a minute. So we just magnify this diagram sufficiently. So this is my principal axis continuum. Okay. So what happens here is this particular refracted ray, its incidence was like this and now it's bending towards the normal. So it appears to be actually coming from a point behind. Appears to be coming from some point like that. So this point now here becomes like the first image, because is as a result of the first refraction, which is happening from where to where, which is happening from air to water. So again, I'll just magnify this a little. So this refraction that is happening from air to water so you can see that this is your refracted ray. It's actually inside water, and I've produced it back to show where it intersects with the principal axis. So it intersects at that point, which we have labeled as I1. So in this diagram, this was your incident ray, and after refraction it's becoming like this. Is this okay? So this is your first event. First event is refraction from air to water at a plane surface. Okay. Just a minute. So this refraction which is happening at a plane surface, air to water, for that the object is which one? The source of light, or S or whatever. And the image is I1. Okay. So further now if I label this distance here, if I label this distance as X, that is the real depth, and label this distance as X prime, that is the apparent depth. So I should get the formula that the apparent depth is equal to real depth divided by refractive index of air with respect to water, because the refraction, remember, is from air to water. So that is the same thing as refraction in refractive index of water into X. So I get the relation that this X prime is equal to 4 by 3 times X. That is my first formula. So actually you will realize now my problem is almost solved, because next step what I want is that, I'm really magnifying this a lot now. So next step what I want is that here this should be normal incidence. यहाँ पे जो reflection हो रहा है, this should be normal incidence. So that what happens now is that this retraces its path. This goes back like this, and if this retraces its path, then this will automatically retrace its path. So the same pair of angle of incidence and refraction. So finally, your image will be formed over here. So your final image will be formed over here. Okay. So hope this is clear. So this is what I want. Okay. I want that the rays which come from air bend into water and then are incident on the mirror here, they should retrace their path. And then automatically the second refraction that is happening from water to air, that will also retrace its path. And finally your final image will be where the source is. Okay. So this is what I require over here in this situation. If I want the final image to coincide with the original object, this is the only way that can happen. It's not just these rays, that particular ray. Even these rays which are coming, some rays coming from here. There's an incident ray coming like this. Then after refraction, it's going like this. Then it should retrace its path so that it comes back like this. So for the second event, which is reflection at the concave mirror. The reflected rays should retrace the path of the incident rays. Okay. So that means there should be what? There should be normal incidence. So now if you go back to what we had discussed earlier, for a concave mirror, normal incidence का मतलब क्या है? The object should be where? At the center of curvature. So this will occur when the object is at the center of curvature for the mirror. Okay. Now what is the object for this one? This object is actually I1. Because see where the incident rays are coming from for the mirror. The incident rays for the mirror are inside the water. So if you produce them back, they are not coming from S. They are coming from that point above, which is I1. So as far as the mirror is concerned, because it's underwater, so it's seeing S as I1. It's not seeing S as S. It's seeing it behind that I1. So the object is I1. Now what about the object distance? It is this distance X prime, which is up to here, plus this height. So there is also this height to contend with, because the pole of the mirror is here. This is the pole of the mirror. So there is also this height h. So the object distance of the point I1 from the pole of the mirror is not x prime, it is x prime plus h. Okay. So that means I1 should be at the center of curvature. So that means I1p should be equal to the radius. How much is I1p? It is x prime plus h. And how much is the radius? 60 centimeters. And itself, how much is x prime? It is 4 by 3x. We had just seen. So plus 2 centimeters should be equal to 60 centimeters. So you can see that here x will become 3/4 of 60 minus 2. So that is 45 minus 1.5. So that is 43.5. X, which was this. So now we have to find what distance? We have to find OP. So that will become x plus h. So that will become 45.5. So this should be my final answer. The distance OP. Okay. Now notice here that I'm not worried about the third thing. Okay. Why I'm not worried about the third thing is, see, if after the reflection these rays are retracing their path, then the following thing that will also happen, that will also retrace its path. The principle of reversibility of light. So here, if this is retracing its path, this is becoming this. The next, this will also become this. This will also retrace its path. This was coming like this, and the refracted ray was here. So the refraction that was happening from air to water, now in water those rays are retracing. So those incident rays will now become these refracted rays. And this is the same pair of angle of incidence and angle of reflected. So they are retracing their path. Okay. So what we have utilized that within the question. So that's why we have not done any calculation for the third refraction. For the third event, that is refraction from water to air, the refracted rays simply retrace the path of the original incident rays in air coming from S. This is by the principle of reversibility. Okay, so I've given you the very detailed explanation and all, but solving wise it's very easy. It's just that one equation, as you can see. So principle of reversibility, let me just elaborate a little bit before. So principle of reversibility is something like this, that if you have this refracting surface which is separating mu2 with respect to, on this side, mu1, and at some point you have an incidence which is like this, let's say, and a refraction like this. Now this will work both ways. If the light is coming this way and this angle is alpha and this angle is beta, so mu2 to mu1, sorry, medium 1 to medium 2, we will have mu1 sine alpha is equal to mu2 sine beta. This is the angle of incidence and this is the angle of refraction. Okay. But on the other hand, if we have a situation where this is happening, the ray is actually coming this way, but at an angle of incidence equal to beta, then you can be sure that they will go this way by Snell's law. Okay. But for medium 2 to 1, now if your angle of incidence is beta, then your angle of refraction will have to be added. Why? Because again, mu2 sine beta will have to be equal to mu1 sine r, and this will show you, comparing with the above equation, that r is equal to r. So this is the principle of reversibility of light applied to refraction. Okay, so I will just minimize this a little and take you right from the diagram onwards up to the calculation below. Yes. It's just taking you through the calculation below. That was the first event. Now the second event is the critical one. This is where it's important to understand what's happening over here. Normal incidence, so that the rays retrace their path. Okay, so the calculation part for normal incidence is just that I1 should be at the center of curvature. So I1P should be equal to the radius. Okay, people, so hope this should be clear. So with this again, you will see that there are certain types of questions in HCV which will be able to solve. This is what I was explaining to you about reversibility, why we don't have to worry about the third event. Because the moment the second event, which is the reflection, is resulting in retracing of the optical path of the rays, the subsequent events will automatically retrace. So in this case, there's only one subsequent event, which is refraction again from water to air. So that particular situation will again result in retracing the paths. Okay. So this will further take care of some of the type of questions which you are doing. Now, in between, you'll notice that there are some odd type of questions which are not going to be solved by either of these, okay, because they don't involve. See, everything that we are solving by this formula-based method, whether we are using the UV formula for mirrors or we are using the real depth apparent depth formula for the refraction and plane surface, we are always solving for paraxial rays. Now, what happens in the case where there are non-paraxial rays involved? Okay? So, situations with non-paraxial rays considered. So as a very simple example, there is question related to this in your booklet, something like this, that you have, let's say, a concave, or we can actually, let's for variety, just let's take a convex mirror. We've been taking concave for very long now. So I'm getting bored of this. Okay. So let us take a convex mirror like this. And this is the principal axis. So this is the center of curvature, and let us now say, so it has a radius of 60 centimeters. Now let us say that we have an incident ray which is parallel to the principal axis. We have one incident ray like this and another incident ray which is just along the principal axis. So I'm just drawing it aside so that we don't have to overlap the things. But so we have two incident rays like this. Let's say incident ray 1 and incident ray 2, but they are parallel to the principal axis, but the gap between them, this gap is d. Okay, and there are only two incident rays in the diagram. There's no third incident ray. So suppose this distance d is given to me as, let's say, whatever, maybe 20 centimeters. Okay, so this is given. Now we have to find the position. So in fact, forget find position. First, let us trace the reflected rays in the above diagram. Okay. And from that, you find the position and type, that is whether it is virtual or real, of the image formed by the reflected rays. Okay. So here we'll understand that rays 1 and 2 are parallel to principal axis such that ray 2 actually coincides with it. Okay. So let's start with the ray diagram. Okay, and let's see what we can figure out from that. So just work this out and tell me what answer you should get. So I'm waiting for your messages. See, highly diminished at focus only would have been the correct answer, but that would have been if they were paraxial rays. Okay. Now here you will see that they are not paraxial rays because it's not very close to the principal axis. That is the whole point over here. Okay. So if we go by the UV formula, 1 by V plus 1 by U is equal to 1 by F, which is 2 by R. You could say that, okay, parallel ray is coming from infinity. So the position of the image should be F, which is R by 2. But remember that this formula is only for paraxial rays. Okay, this is only applicable for paraxial rays, for which the angle of incidence is small angle. So that we can substitute sin I as I, and that kind of thing. Or we could substitute alpha, beta, gamma in terms of, arc lengths and all that. Now here if you see, that is not happening because, here that particular situation is not happening because this ray is actually very far from the principal axis. It's parallel to the principal axis, no doubt, but it's far. So when it's incident at this point over here, draw normal. So center of curvature, this is the normal. So this is my angle of incidence theta. So you'll have to bend like this now after reflection that this angle becomes theta. Okay. Now we can see what this theta is. Okay. This distance is d. Okay. So in this diagram, you can see this angle is also theta. If you just drop a perpendicular from here, you'll be able to understand what is this. This is r, this is d. So theta is sine inverse d by r. So it is how much? It is 1 by 3. Sine theta is 1 by 3. So it's definitely not a small angle. So now how do I find the position of the image? So for that, I'll have to retrace the path of the reflected ray, which is this one. So retrace the reflected ray that is meeting the principal axis over here at some position I, like this. Okay. And the other one is coinciding with the principal axis. So that ray is just going like this and retracing its path. So these two are intersecting here. So that becomes the image position. So now use this diagram and try to find out how much is pi. Okay. So now find out pi, and you will see it will definitely not come out to be 30 centimeters, which is the focal point. You will see that the focal point in this diagram probably should be somewhere here. Okay. Whereas on the other hand, if my second ray had been like this, had it been very close to the principal axis somewhere over here, then those would have coincided at the focal point. You would have got a virtual image at the focal point behind. But these are not paraxial rays, so they do not actually. In fact, if we had an entire set of rays like this, you would not have got a definite image. It would have been a very blurry kind of image. But here we are just talking about two specific rays. One, we are imagining that kind of thing, that we have very specific focused rays like the type you would have in the case of a laser or something like that. So you have two laser rays which are highly directional, and one is parallel to the principal axis at 20 centimeters and the other is along the principal axis. So the one which is parallel to the principal axis, it diverges in this manner over here. So it diverges in such a way that it will tend to show you an image or a point of intersection when produced back at this point I, and you can show that pi will in fact not be equal to the focal length or 30 centimeters. So this is where one has to be a little bit careful when we are dealing with non-standard situations, and that can happen very often in JEE advanced type of papers. It will not happen in JEE mains. You will typically get formula based questions. Okay, but in JEE advanced type of papers, you will often come across a situation where we are not talking about normal line of sight or paraxial rays or things like that. So there you have to go back to the fundamentals. Here, what is the fundamental? That angle of reflection is equal to angle of incidence. Nothing else. No small angle approximation is used. Okay. So to understand this now, let's come to this diagram in detail. Okay. So I'm just magnifying this diagram here as much as I can. So in this diagram, you can see that this angle here, this angle is how much? It is 2 theta. No, because this the refracted ray, reflected ray produced backwards. And this reflected ray, this was parallel to the principal axis, and it's now at an angle of 2 theta. This whole angle is 2 theta. So that's why this angle is 2 theta. Okay. So based on that, and this distance is d over here. So based on that, we can find out how much this distance is. So I've dropped this perpendicular from here, and this perpendicular distance was d. Okay. So now let us say I want to find out this distance here. So let me just tidy this up a little. So let's show this angle here only. It is 2 theta. Okay. Now let us talk about this distance here, this one. This. Okay. So we have x such that x by d is equal to cot 2 theta. So we'll make use of this. Right. And you also have to calculate this distance here. This one, principal axis to this. I mean, whole point to this. Let us say this is y. So you also have to calculate y separately, which we'll do. Don't worry. So y will come from arc length concept. Okay. But let's focus on the x first. Okay. So hope the diagram is clear to you. I'm magnifying it a little bit more now. So first, just make sure you understand the angles and everything. Then come to the trigonometry part. Yeah, Aditya, I think your answer appears to be correct. Okay, so now let's come down to the calculation. So let's start with x first. So x is equal to d cot 2 theta. Okay, so that we can write as what? We can write it as d cos 2 theta upon sin 2 theta. So 1 minus 2 sin square theta upon sin 2 theta, that is 2 sin theta cos theta. You can do like this. Okay, and we have sin theta is equal to 1 by 3. So cos theta becomes how much? 2 root 2 by 3. Square root of 8 by 9. So substitute that here. So D was 20 centimeters into 1 minus sine square theta. So that's 1 by 9 divided by 2 sine theta cos theta. So 2 times 1 by 3 into 2 root 2 by 3. So this will actually become 20 into 8 by 9, but the 9 will cancel in the denominator, divided by 4 root 2. Okay, so it is actually 20 root 2, or approximately 28.8 centimeters. You can just check my calculation, but this is what I'm getting. It is 2 sin square theta. Okay, sorry. So there is a factor of 2 by 9. Yeah, correct. So make a small correction here. This step here, it is 2 by 9. Okay, so this is now becoming how much? This is becoming 7 by 4. Okay. So this will become 5. So 35 by root 2, or 35 by 2 into root 2. So that I'll tell you how much it is approximately. 17.5 into 1.4 approximately. Yeah, so that will come approximately 24.5. That is just the value of x alone. Now we still have to find the value of y over there. So I'm coming to that. So thanks Ashwin for that correction. Alright, so clear so far. Now let us find out the value of y. So y के लिए देखो क्या करेंगे? We'll just use geometry. This was a mirror. This was my principal axis. This point of center of curvature, this point of pole. Now my other ray, which was incident, now I'm drawing it with a different color. So that was over here, and after reflection it became something like this. So this angle was 2 theta, and we produced this back and all that. But now we are actually interested in this. We dropped a perpendicular here, and we are interested in this distance. Okay, so this distance is our y, and as you can see, it will become PC minus this quantity. Produce this back. This angle is theta. This is r. So this is how much? This is r cos theta. So is that r minus r cos theta? So that distance y is r into 1 minus cos theta, like that. Okay. So it is 60. So it's equal to 60 into 1 minus 2 root 2 by 3, that kind of thing. So y will be approximately, I'll tell you. So if we take root 2 as again 1.4, so that is 2.8 by 3. And you subtract that from 1, so we get nearly 0.07, and multiply that with 60, so that you get nearly as 4 centimeters. Okay. So in fact, this comes very close to 4 centimeters. So this is multiplied with lengths. This kind of calculation. So now my distance pi is basically y plus x. So that is 4 plus 24.5. You can see it's not quite at this thing focal point. It's slightly behind the focal point. Whereas my focal length was 30 centimeters. So, if I take the parallel ray even further up, like here D was 1/3 of the radius. If I take it as half of the radius or something, this discrepancy will become more and more significant. Whereas if I reduce the value of D, suppose I had taken D as something like 5 centimeters or something over here, the calculation would be much more involved, because you would get very small values of theta and all that. But doing the exact calculation, you would have seen that it would have merged with 30 centimeters. So the closer that parallel ray is to your principal axis, the closer your answer will be to the actual focal point. And the further you take it away up, what is happening? The more it is actually coming towards the pole, and the more your approximation is failing actually. So hope this calculation is clear. So the calculation is lengthy, but the concept you can see is very simple, that we are just using law of reflection. Just that odd values of sine theta, cos theta, that all took time. But the simple thing is this ray diagram. Just understanding this ray diagram is the key. This one. So you see that if I take a ray somewhere over here at a distance of 5 centimeters or 2.5 centimeters, the closer I come to the principal axis, the closer this actual point I will go to the focal point. So that is why when we consider paraxial rays, we get a very well-defined image at the focal point. But the moment we are going away from the principal axis, even though the rays are parallel to it, they are no longer paraxial rays, because they are going to sort of diverge off and give you a very blurry kind of image. They're not going to give you a very sharp image. And that blurry image will be away from the focal point. All right, so this is one of the variation questions I was telling you about, where we make use of the fundamental principles rather than the this thing. rather than the derived formulas which are coming for Paraxial Rays. Okay, now let's look at one more very interesting question from H.C. Verma, which I'm sure some of you have tried out, though as of now I have not received it as a doubt from anybody on WhatsApp yet. Not in this batch, but I have received it as a doubt from others. So it's a very interesting problem. We are going to learn a little bit about optics from this. So there is, I'll tell you the question number. I just have to open the book, but it's unmistakable, this question. So these are opaque walls of, you can see, a well kind of thing, such that now there's an observer somewhere over here and his line of sight is like this. Just hang on till I complete the diagram and I explain what it is. So this dotted line actually represents the line of sight for an observer's eye. Some kind of an observer who's present over here. This is his line of sight. That so happens that his line of sight actually is at an angle of 45 degrees. Like this. Okay. And since this wall is opaque, therefore, he cannot see anything on the floor, more or less. He can just see the corner of the floor. He cannot really see anything on the floor otherwise. Okay. You realize, just imagine this is an opaque wall. No? So he's just able to see this corner. He's not able to see anything over here. Now, interestingly, what's happening? We have a point object which is placed somewhere over here. And I'll just give you the location of that point object. And he's not able to see that point object. But if he fills water up to a certain height, the refraction will help him and he'll be able to see. For a certain minimum height, he'll now be able to see this. Okay, so let's say the length of this container's walls is L, and something else is given to you. Now, so let me just find the question while we note down the diagram. Yeah, so this is question number 24. Okay. So it's a cylindrical vessel actually. So the diameter of the cylindrical vessel is equal to the length. Okay. So these are the opaque walls of cylindrical vessel. So the length of the sides is equal to the diameter of the floor, and that is equal to 30 centimeters. Okay. And that point object P is given to us at a distance of 5 centimeters from the center. So if the center of the floor is over here, and the floor is actually this kind of a vessel. So that point object is here. So P is a point object at 5 centimeters from the center of the floor, okay, center of the base. So we have to find up to what minimum height H water, which has a refractive index of 4/3, must be filled so that that point object P is visible to the observer. In the original question, that angle 45 is not given to you, but the diagram shows you the line of sight, and since L is equal to the diameter of the floor, that is given to you. So you can actually figure out that that angle is 45. Okay. So like I've already given you a hint for the question. Okay. So this is the entire question. In case you don't have HC Verma in front of you, you can just take down the question. But now we'll understand in a moment why, if you fill water, there's a possibility that you can see a point object like that. Okay. So this is again about refraction, but refraction of rays which are not paraxial rays. So just take down the data of the question if you don't have HCV in front, and I'll give you a hint of how to attempt this question now. So in this question, we cannot use the concept of real depth, apparent depth, because you are not seeing the object from vertically above it. You're seeing it from a different line of sight. You're seeing it like this, from a diagonal side. You're not seeing it from a kind of normal line of sight above. So forget about applying the apparent depth, real depth formula in this. Okay. So the hint to you in this question and other questions like this is that if you have a container like this, which is filled with some kind of a liquid, and we have some kind of a point object at the bottom, then the rays of light which are coming from the point object, they bend away from the normal like this. They bend away from the normal in such a way that you have this formula that if this angle is I and this angle is R, then refractive index of water into sin I is equal to sin R. This is the fundamental principle that we can apply, and that's the only thing from optics we can apply. The rest is geometry. Here we cannot apply any small angle approximation that sin I is equal to tan I, and therefore real depth upon apparent depth is mu and all that. We have to stick to the fundamentals. Okay. So just use this as a hint to now work out this question, or understand how this will fit in this ray diagram. So first, just try and figure out in the ray diagram now how you can fill water up to a certain height so that that point just comes in as field of view. Okay, so let's tackle this question now, people. Aditya, you can just check your answer. It's HC Verma question number, I think it was 24 or whatever. We just check and tell you. Yeah, question 24. The answer is 26.7 centimeters. Okay, 26.7. So we'll be able to do an exact calculation. So let us come to sort of magnified version of this diagram. So in this diagram, what I want now is that my water level should be, let's say, up somewhere here. So water level should be up here so that this refracted ray which is coming along a line of sight limiting case, the one that is just about the last one you can see is coming from this point. So the incident ray for that refracted ray is actually this one. This should be the incident ray. Okay. So this is how the bending should happen. And this is nothing to do with where the center of it is. Okay, that's just for the distance. We'll come to that later. So now if I drop a normal over here, let's do that next. So at the point of incidence, this is my normal. Okay, so now this is where the entire geometry is within this diagram. So we'll see that if this is our angle of refraction, this is our angle of incidence. Now you can see that this refracted ray is a continuation of this line. So what is my angle of refraction? It is this angle. It's 45 degrees. So R you can immediately see is equal to 45 degrees. So I we have to find out how much it should be so that this point is visible. Okay. Now for this point to be visible, we have to also understand one thing over here. This geometry, that this is a 45-degree triangle, this one. So whatever this distance is, x suppose, this is the same. And x plus h is equal to nothing but the total length, which was this. So that's one thing that we have. Okay. And then the other thing that we have is that already we know that this is 5 centimeters from the center. That means from this end, is that how much? It's this thing. Center to this end is how much was this? 30 centimeters, the length. Yeah. So 15 centimeters here. So ye kitna? 10 hai. So that means this length over here is how much? It is 20. So this length over here is 20 centimeters because it is 5 centimeters beyond the center. The center is at 15 centimeters per moment because length was given to us as this. So we know that now. Okay. So this is where our geometry comes in now. So now further, you can see that in this triangle, this side is suppose small a or whatever, and this height is h. So we have this triangle. Sin I is according to that. Okay. So we have to make use of Snell's law, we have to make use of this, and we have to make use of this geometry. So just understand this diagram fully once, and then let us see when we apply Snell's law what we get. So by application of Snell's law next, you see over here we get mu of water into sin I is equal to sin R. Okay. This too we have to find out. This we already know, and we also can see in the diagram that h by E is cot I, and E itself is how much? E itself is 20 minus x. So all this information is known. So let's try to fit that into a formula. So everything finally we have to reduce in terms of h. Okay, so let me refer back to that diagram, see what we can pick up from here. So in this diagram we can see that tan I is equal to A upon h. And further you can see what is E in that diagram. E is 20 centimeters minus x. Like this. And we also have the relation that h plus x is equal to 30 centimeters. So further we can write tan I as 20 minus x, and x itself is 30 minus h. So this will become how much? It will become 20 minus of 30 minus h. So it will become h minus 10 divided by h. We substitute that here. Okay. So this is my equation 1, which is just coming from trigonometry and geometry. Okay. Now Snell's law is telling me 4 by 3 sin I is equal to sin 45. So it is telling me that sin I is equal to how much? It is 3 by 4. That's my second equation. Okay. And now just solve these two. So you can write tan I in terms of sin I. So I'm just maximizing this a little more now. Okay. So for example, if I take equation 1 and square it, so I have tan square I, and on the other side it was, I think, 10 h minus 10. So h minus 10 divided by h ka whole square. Okay. So this is sin square I upon 1 minus cos square I. So it's sine square I upon, sorry, cos square, so 1 minus sine square I. So is equal to h minus 10 upon h power whole square. Okay, so this equation you have. And equation 2 was that sine I was 3 by 4 root 2, correct? So substitute now. So you can see 3 upon 4 root 2 ka whole square upon 1 minus 3 upon 4 root 2 whole square is equal to this thing. Later we'll take the square root of the whole thing, so don't have to really solve a quadratic equation. So if we just take LCM and cancel out the common denominator in this thing and so this will be how much? 16 to the 32 minus 9. So 32 minus 9 is how much? 23. Is this correct? So this should become equal to, so square root of this should become equal to h minus 10 by h. And from this you calculate the value of h. Then you should get your answer. So these questions are a bit painstaking, and you have to be prepared to dig in and do the calculation fully and all this. Okay. But it's rewarding in the sense that you will properly learn the geometrical optics aspects through it. Right, so question 22, 23, 24, these are all tricky sort of questions. But now if you just review through the ones that we have done in today's session, you will be able to apply the same methods. And if you are still stuck with the calculation in something, you can always WhatsApp me. I will send you the hint or whatever formula is required, etc. But I'm confident that you will be able to deal with these questions now after you have completed today's lecture. So a couple of more tricks we still have to discuss today's lecture. Okay. So, for example, there's another question in HCV, which is something like this. I'm not doing the whole question, but just giving you an idea about it. So you have like a vertical pole, which is of a certain height, and it's standing under water. So the water is up to a certain level. So we know the height of the water level, and we know its refractive index is 4 by 3. Now it says that sunlight is incident on it at a certain angle. So sunlight is incident here at a certain angle. Okay. And we have to find the length of the shadow cast. So we want to find, given the length of the pole, the height of the water column, sorry, all this is given. So given the length, refractive index of water, and also this angle at which the sunlight is falling. So it's late evening or something, so it's slanted. So given theta also, we have to find the length of the shadow that is cast in the floor underwater. So for that, you have to just understand that, just imagine a ray of light which is just about missing the surface. I mean, missing the top of the pole. If it's going like this, then after refraction, it will go something like this. So that ray of light is giving you a bright sunlit thing over here. All these rays are also doing the same. They are giving you bright sunlight in this part of the floor. Okay. And similarly, the rays coming like this over here, they're also giving you, so this part is all lit. But ये वाले rays जो है, यहाँ से लेके यहाँ तक जो rays incident है, some of them are incident above water, some of them are incident under water, like this one. They are not giving you. So the shadow is this long. This is the shadow. So geometrically you have to calculate this. For this critical ray, this one, for this critical ray, you have to calculate this angle of incidence, this angle of refraction. Now you know this height, so from this you can calculate this distance. You know the geometry, so you can calculate this distance. So you can calculate the length of the shadow, which I have shown below. And just illustrate the shadow length with a different color. Okay. So you know this last ray is just about touching the top of this. This one is coming and putting sunlight here. But before this, there's nothing. There's no light because the rod or the wall or whatever is blocking it. So this is your shadow length. Similarly, there's a question like this, that on water there's a tire floating and there's a point source of light underwater, so it casts a shadow on the ceiling above. So all these type of questions, this is the common method of solving them. All right, next we'll see another very important application of refraction at plane surface. We will see refraction due to a transparent slab. Okay, so it turns out that this works out into a very convenient formula. And we'll do the derivation of that formula and we'll understand applications also. So it so turns out that if I have a slab which is shape-wise, you know, it's bounded by two parallel surfaces, and the thickness of the slab is T, and it's a glass slab or something, so its refractive index is mu. Okay. Now, for any point object kept on one side of it, for normal line of sight from this side. So again, this guy has a normal line of sight. Okay. That object will actually appear to be here. It will appear to be closer, and this is called the lateral shift along the principal axis. So as it turns out, this lateral shift will actually be equal to the thickness of the slab into 1 minus 1 by mu. Okay, so we're going to do a derivation of this formula just now, but this also effectively becomes a very useful formula to use as a shortcut. So anytime we have a slab in between, the lateral shift is like this, and very interestingly, the lateral shift is independent of the object's distance from the slab. So whether the object is here or it is somewhere behind or somewhere front, the amount by which the image is shifted with respect to the object, that remains independent of that. That only depends on the two things of the slab, the two properties of the slab, the thickness and the refractive index. Okay, so just make a note of this formula, then we'll discuss its derivation and application. Okay, so let's quickly understand the derivation of the formula. So again, the derivation actually comes from what is happening in terms of fundamentals. It is refraction at two surfaces which are both plane, okay, and it is normal line of sight. So we can use the real depth apparent depth formula. So if you consider the point object over here, let's say, this is our normal. Now again, in my diagram, I will show rays which are a bit divergent, but you will have to understand that they actually represent the paraxial rays. So imagine they are very close to the principal axis, making very small angle. So consider an incident ray over here like this. What will happen? This will bend into the glass towards the normal. So as it bends towards the normal, the first event that you are getting is refraction from air to glass. So when you produce this back, this gives you a supposed image over here, I1. So this is the first refraction. Then what happens? This incident ray, this refracted ray is incident at this point, and it appears to be coming from I1. So there is again a bending, but this time away from the normal. And because these are two parallel sides, actually you see the pair of I and R and the pair of R and I here are same. So this ray that emerges out, the so-called emergent ray, is actually parallel to this incident ray. And this incident ray, this one, if you produce this forward, that and this are actually parallel. So that is why when you produce this back, this will meet somewhere here. And this is where your final image I2 is. So this is your final image. Okay. This is the image seen by this guy, because there is rays coming virtually undeviated from here, and the rays which are slightly away from the principal axis are coming slightly more divergent. So his eye collects those paraxial rays and they appear to be coming from this point I2. Okay. So now let us just apply the formulae for both the things happening end to end. Okay. So just a second. Yeah, so if we just apply the formulae for both the events happening end to end. Yeah. So in this diagram now, let us say that the original object is at a distance x like this from this. Okay. And after the first refraction, the apparent depth becomes x1. That is this. Okay. So the first event, it is from air to glass. So the apparent depth, which is x1, will become real depth, which is x, divided by refractive index of air with respect to glass. So that means x1 will become mu x. So this is the solution of the first event. Okay. Now let's come to the second event. Now for the second event, what is happening here is that the object is no longer this O. The object is which one? I1. And the refraction is happening where? It is happening at the second surface. So if this thickness is T, now you can see for the second refraction, this is the incident ray. So this is coming from where? This is coming from I1. So what is the real depth? It is this one. This thing is the real depth. Let's say this is Y. And you can see Y is nothing but x1 plus T. And this causes refraction like this, and I2 becomes the image. So let us say the distance of I2 from this end, that is my Y prime. Okay. So the second event, it is refraction from glass to air. So the apparent depth, which is y prime, should be equal to the real depth divided by refractive index of glass with respect to air. So that means y prime will be equal to y divided by mu, where mu is the refractive index of glass. Now what was y itself? We had seen in the diagram earlier. It was x1 plus the thickness. In the ray diagram, you can see that this image I1 of the first refraction, that is becoming the object for the second event. So that is at an actual depth of how much? x1 plus the thickness. And x1 itself from equation was 1 was how much? Mu x. Okay. So further substituting, y prime becomes mu x plus t by mu. Okay. Or you can write as x plus t by mu. That is my y prime. Now I've actually got the position of the final image, because that I2 is nothing but my final image, but I have to find its shift with respect to what? The original object. So going back to this diagram, now I have to find which distance. I have to find this one. I have to find this distance. This is delta x. Okay. And this distance is nothing but my y prime, which we got just now. And this distance is nothing but x plus the thickness. So I'll just minimize this a little and the distances will become clear to me. Okay. So remember, x is not the distance of O from I2. X is the distance of O from the first surface over here, this one. Okay. Whereas this y prime is not from, it's not the thickness of the slab, it's where I2 is located with respect to this surface. If you magnify this diagram a little more, you'll understand that difference. All right. So let's now come back to this. So we want to find out delta x, which in the diagram you can see is this distance, this whole distance, which is x plus the thickness minus y prime, the distance of I2 from this point. So delta x, the shift of the final image with respect to the object, is x plus the thickness minus y prime. So that is x plus the thickness and as expected, it gives us what we had seen earlier. It is independent of x. It is independent of the object distance and is given by this formula. So this is like a direct application formula that you should use, just like we use the real depth apparent formula. But instead of refraction at a single plane surface, when we have refraction due to a slab with parallel surfaces, you should use this formula. So the type of questions where this becomes very useful is something like this. For example, if we have something like this.
I'm just saying I like.
So this has a thickness of, let us say, 2.4 centimeters and is made of refractive index of material 1.5, and this has a thickness, let us say 6 centimeters. And this is made of material which has refractive index, let us say 1.2. And now there is a point object over here which is kept at some kind of distance, 10 centimeters, and between these two there is a gap of, let us say, 2 centimeters, and there's an observer who has the normal line of sight. You want to find the position of the image. The position of the object as seen by the observer. This is what we want to do over here. Okay. So here, if we went by the fundamental method of solving by ray diagram, we'd have to solve 1 refraction, 2 refraction, 3rd refraction, and 4th refraction. So 4 times we would have to calculate real depth, apparent depth, keep adjusting using the distances in between and everything, and it would become a very messy calculation. But what we can do here is just use the slab formula directly. So if my observer had been in between the 2 slabs, he would have seen the refraction only because of 1 slab. So that would have created a certain amount of shift, and then that would become the object for the 2nd slab. So for the 2nd slab, the object is already shifted by a certain amount, and it's shifting it further by a certain amount. So my final image would be somewhere here, let's say, where this distance from here to here, you can say, is the net amount of shift. So that net amount of shift, because it is independent of object distance, now only it depends on the thickness of the slab and the refractive index. It is just shift because of slab 1 plus shift because of slab 2. So it is equal to T1 1 minus 1 by mu 1 plus T2 into 1 minus 1 by mu 2. So this net shift here, you will see, will become 2.4, and the refractive index is 1.5 or 3 by 2. So this will become by 3 plus 6 into 1 minus 1 upon 1.2. Now 1.2 is 5 by 6, so 1 minus 5 by 6 will become, 1.2 is 6 by 5. So 1 by mu will become 5 by 6. So this will become 6 by 6. Okay, so this is becoming 0.8 plus 1. So the shift will be by 1.8 centimeters. And now we want to find the distance in terms of from the slab, how much it is and all that. You can just add and subtract whatever is required. You will get the answer. Okay. So this is a typical type of question where it's very important to apply this direct formula and this direct trick, that each slab produces a shift according to its thickness and its refractive index, and nothing to do with any other dimension or nothing to do with any other distance. So hope this formula is clear to you guys. And how we've applied it, more important. So the very interesting thing about this is that the shift that we are getting, it is independent of this distance. If the distance between the 2 slabs is d, and also the distance of the object from the first slab is x. So it's very important to understand here that delta x is independent of d and x. Okay, now why this is important to understand it's independent of these two, because then we can understand, we can apply it in a case like this, which I'm showing next. So we have a case like this where we have two slabs which are actually against each other. So this has some kind of a thickness, let's say 3.6 centimeters, and some kind of a refractive index 3/2, and this has some kind of a thickness, let's say 2.4 centimeters, and refractive index 4/3. Okay, and in fact, the point object that we have kept is not even somewhere else; it's right over here. It's over here. This is our point object. And from this side, we want to view where it is. So this time we could do by real depth, apparent depth also, because there are just two events: refraction from mu1 to mu2, and then from mu2 to air. But it is much easier to do it by the shift method, because in the earlier diagram we had seen that if we keep the slabs away from each other, okay, and the object also somewhere here, but still our shift is independent of this x and this d. So now make x tending to 0 and make d tending to 0. Now you brought the two slabs against each other, so the distance between them is tending to 0, has become 0 almost, and this point object is here only, but still your delta x remains the same. It does not get affected by this fact that these two are now tending to 0 or have become practically 0. So your formula and value of delta x will remain the same. So this is the same. So here also my delta x net, so my image of that point will appear somewhere here, where this lateral shift I can just calculate by that formula. Okay. So if you put the values and calculate it here, we have taken this thickness as 3.6 centimeters, and this refractive index as 3/2. So this will become 1/3 of this. This thickness we have taken as 2.4 centimeters, and refractive index 6/5 or 4/3. So this will become 1/4 of that when you substitute. So the total shift will be 1.2 plus 0.6, or it will be 1.8 centimeters. So I know the shift is this much now. So then I can also calculate that, okay, from here, how much distance it is appearing to be. So if this apparent depth is some like x prime, so x prime will just become the actual depth, which is 3.6 plus 2.4 minus delta x. So you can see that x prime will become the actual depth minus the shift. Okay. So the actual depth was the sum of the thicknesses minus 1.8. So that's becoming how much? 6 minus 1.8. So that is 4.2 centimeters. So this point object behind the two slabs, which is at an actual depth of 6 centimeters, will appear to be at a depth of only 4.2 centimeters because of the combined effect of the refraction at both the plane surfaces. Okay. So this was the final trick for the day. So hope things are clear up to this point. So this is where we conclude today's lecture, people. And next time we will start with refraction at spherical surfaces. So we'll understand how to apply Snell's law when the refracting surface bounding two media of refractive index mu1 and mu2 is actually a spherical surface instead of being a plane surface. So the formula changes, and then using that formula we will derive what is called lens maker's formula. That is how to find the focal length of a thin lens using the radii of curvature and the refractive index. So if you want to read ahead, you can go ahead and prepare that part, which is lens maker's formula and refraction at spherical surfaces. Otherwise, just do questions related to these things, which is about up to question. Using all these concepts, you can proceed up to about question 36 in HC1. Okay, I'll send you a detailed listing of questions, but up to about question 36, you can proceed in HC1. And now you can try and do each and every question in this part. Okay, so that's it for today. Hope you've understood and enjoyed this lecture, and stay safe as always, and try to make this time a bit productive. Okay, from your studies point of view. I know it is very frustrating even for me, but anyhow, so good evening, and until next time, that's it guys. Okay, see you again. Bye.